So we've introduced the ideas of Maxwell's equations, and the one big thing that he adds to the whole story is that until we get to the next topic, the one big thing he's added to the whole thing is that he introduces the idea of displacement current. So let's do an example using that. So let's consider that we've got a parallel plate capacitor. So the parallel plate capacitor is composed of two large metal plates. Let's say they have a diameter here of 10 centimeters. And we're charging the capacitor with current here. So one side's becoming positive, one side's becoming negative, and let's say that the charging current is going to be 0.25 amps. Okay, now we know that we can find an expression for the magnetic field at some distance r away from the wire. We've done that. We've already figured out how to find that magnetic field. If we were to find that distance r from way off here to the side of the capacitor, then we simply use the displacement current. But what if we want to find at r equals 5 centimeters, so not all the way out of the capacitor? So is there a magnetic field there? Well, there's got to be a magnetic field there because we're charging the capacitor, so we're changing the electric field in the capacitor, which means we're changing the flux in the capacitor. If we're changing the electric flux in the capacitor, then what we've got is we've got the Ampere-Maxwell relationship. So remember the Ampere-Maxwell integral B dot ds. So integral B dot ds equals mu naught I plus mu naught times the displacement current. Well, the displacement current we also said was epsilon naught, the derivative of the electric flux. And so this right here is our displacement current. So inside the capacitor here, there is no actual charge flowing through the space in the capacitor. So that means that what we've got is this relationship right here. The integral, if we integrate around an imaginary circle here, so if we're always the same distance, 5 centimeters out, everything's cylindrically symmetrical, so the b comes out of the integral, and so what we have here is just 2 pi r times b. Okay, now we did that integral before. Okay, so we did that quite a number of lectures ago. All right, so what we got now is 2 pi rb equals mu naught epsilon naught rate of change of the electric flux. So all we got to do is find out what is the electric flux in there to find its derivative. So the electric flux we know is the integral of E dot dA. Okay, so the electric field inside the capacitor should be pretty well uniform, and so that means it's going to be constant coming out of the integral, so this is going to be just E times A. Okay, and so A is the area around that little circle here that's inside the capacitor, so that's R, so that means it's pi r squared. All right, so that's going to be my electric flux. So the derivative of the electric flux is going to be the derivative of E pi r squared. Well, pi is a constant, r, we're always the same distance in the center, so that all that comes out. So the derivative here is going to be equal to pi r squared, the derivative of E. So now we plug that back in. So we have 2 pi rb, and that's going to be equal to mu naught, okay, times epsilon naught times pi r squared dEdt. So that pi cancels that pi, that r cancels that r. So looks like we're getting close to finding the magnetic field. Mu naught epsilon naught r over 2 times dEdt. Okay, so now all we have to find is what is the electric field in there. Well, let's go back to our definition of what's going on in here. Because remember I said this is basically a capacitor right here. And so we know that for a capacitor, the definition of capacitance is Q over V. Okay, if it's a parallel plate capacitor, we have epsilon naught A over D, and that's going to be Q over V. So we do a little bit of algebra here. V over D equals Q over epsilon naught A. Okay, well, what A? It's the A of the entire capacitor. So that's going to be Q over epsilon naught pi big R squared. So little r was how far out we are. Big R was the radius of the entire capacitor. Okay, now V over D, however, if you remember, V over D is the electric field. So the electric field is going to be Q over epsilon naught pi r squared. So the derivative of that, if I take the derivative of that, that's going to be the derivative of this. Well, everything's constant except for Q. So this is going to be equal to 1 over epsilon naught pi r squared dq dt. Well, dq dt is I. So what that means is we can now say that the derivative dE dt, okay, is going to be equal to 1 over epsilon naught times pi r squared times I. So now we go back and plug all this back in. So B is equal to mu naught epsilon naught r divided by 2. Now we divide by epsilon naught pi r squared. We have I. Okay. Well, the epsilon naughts cancel. Okay. And so what we have here is B is mu naught r I over 2 pi r squared. Okay, and so at that point, we just plug in the numbers that we had. Mu naught, 4 pi times 10 to the minus 7 Tesla meter per amp. R, little r was 5 centimeters, so 0.05 meters. We had 0.25 amps. Divide by 2 pi 0.1 meters squared. And so the magnetic field comes out to be 0.25 microtesla. So that's the magnetic field at that spot that is 5 centimeters away from the center of that capacitor that we're charging. So again, we got this capacitor here. We're charging the capacitor. We got current flowing in and out. The capacitor has a radius of 0.1 meters, and we're looking at a spot here inside the capacitor that's about halfway out from the center. Clearly, you can also see what happens if little r is 0. So in other words, if we're in the dead center of the capacitor, the magnetic field is going to be 0. And so, and then at the edge of the capacitor up here, where little r equals r, is going to be just mu naught I over 2 pi r. Now, from that point out, it's just going to be mu naught I over 2 pi little r, where little r is the distance out. So now we have an expression here for the magnetic field as a function of the distance from the center.